Thank you everybody for coming. So this is going to be a little bit different from a lot of talks because it actually doesn't really have anything to do with Python, except that what I really want to do here, accomplish at a Python conference, is talk with people about how the stuff that I do, which is very low-level C++ high-performance stuff, can impact and benefit people in the Python community. How can this tie into Python projects like NumPy and SciPy and SciPy and things like that? And how can what I do be changed to benefit you guys more? So the topic is BLAS and tensors, but what is a BLAS and a tensor? It's like that a stress ball thingy, right? So what are those? So BLAS is basically how you do matrix operations. So think a matrix is like a square array, it has some data in it, and you do a matrix multiplication. Well, that's BLAS. And mathematically, it looks like that. You multiply some things together, and then you add them up, and you put them in the output. That's matrix multiplication. So tensor contraction is actually very, very similar to this. All you have to do is you take your tensors, which are now multi-dimensional arrays, and where the dimensionality of your tensor can be 0, 1, 2, 3, up to any number, and you're going to be multiplying elements together, and you're going to be adding them up and putting them in the output. And so aside from having a lot more dimensions here, it looks exactly like matrix multiplication. The problem is, if you want to do matrix multiplication, you use BLAS. If you want to do tensor contraction, what do? There's no library. You can't just go out and get a tensor BLAS. So that's what I'm going to be here to talk to you about. So who am I? I am a chemist by training and by roughly about half of what I do for my day job. So I worry about things like molecules. Okay, so maybe I want to find out what is the single triplet splitting of this organic molecule so I can know whether it's going to be good for photonic applications or something. Or, what is the electronic spectrum of this thing, or what is the kinetics of this system. And to do this, I have to do lots of math, as you might expect. And the math, the form that this math takes, happens to be almost all the time tensor contractions. So that's why I'm concerned with doing tensor contractions and doing them fast. So how do I have to do these tensor contractions? Problem is, it's complicated. So let's say I start with something simple, something from linear algebra. I'm doing a diagonalization of a matrix, okay? And in quantum mechanics, basically what this gives you is it gives you an energy. The matrix is your Hamiltonian, the vector is your wave function, and the scalar is your energy. So it's just linear algebra, right? It's simple. The problem is that the matrix and the vector aren't really a matrix and a vector. They're collections of tensors. Those tensors are sometimes defined as contractions of other tensors. Now we have a lot more tensors. And then those tensors have structure to them. They're not all, they're not rectangular or dense tensors, if you will. They have lots of zeros in them. So you have to worry about that structure. You have what's called permutational symmetry. So if you think of like a symmetric or an antisymmetric matrix, it's like that, but for tensors. Now you have lots of dimensions. You have lots of different types of symmetries you could have. And you have to deal with those. And then these things are huge. So you have to slice them or block them or whatever to even get them to fit in memory. And then you have to slice them and block them more to get them to fit into something that you can compute with. And then there's more kinds of sparsity you can put on top of that. And then eventually you get down to something which is a matrix. And you multiply those together and you call BLAS. And so at the end of the day, what I do is I do this. And the largest number of BLAS calls I've ever done in one job was about 10 billion. So I did 10 billion individual BLAS calls, matrix multiplications, over the span of about 2 days. And so they're each, if you do 10 billion gems, they're not going to be efficient. Why are you even calling them KL? You could just write some loops, right? And so can you do better than this? The first step to doing better than that is what I'm talking about today. There are lots more layers here, which I'm interested, but perhaps other people are not quite so interested. But tensors are not just in chemistry. There's tensors in a lot of different fields. For example, machine learning, imaging, physics, computer vision, engineering, lots of things. Hopefully some people here have some idea what tensors are. They're like, oh, I use tensors. I like this talk. Maybe that's why you're in this room. That would be nice. And so what I want to talk about is not the chemistry part of it. It's what is the fundamental unit of tensor computation, or at least tensor contraction. How do we define an interface for that? And how do we do that fast so that people can take advantage of it? So interfaces are key. So everyone knows, hopefully everyone knows what the BLAS is, what the BLAS interface does, what parts it has. And love it or hate it, that's the interface, right? If you want to do matrix multiplication, that's what you use. So what are the kinds of things we have to think about when defining an interface for tensors? So why does BLAS work? Why is it good? So here's a typical BLAS call. This is a matrix multiplication, and it has these various different parts. And so the major division between these parts is the specification, what operation am I doing, and the data, what am I doing this operation on. So I need to know what are the sizes of these matrices. Have they been transposed or conjugated or information transposed? And then I have to know, on the other hand, where is my data in memory and how is it laid out? So if I know these two things, then I can do the matrix multiplication. And everything is right here in this one call. There's nothing hidden, no global variables, no objects, no anything. Everything is right there in that one call. And from a high-level usability perspective, that's not really that great. But this is at the very bottom. You can build on top of that. You build layers and layers and layers. And eventually you get up to something that people can use efficiently. And this is something that the computer can do efficiently. But why does BLAS not work? When does BLAS not work? What are some things that we've learned in the past 25 years that maybe we wish we could have done better? So, okay, we'll look at these transpose parameters. What happens if we want to do conjugation without transpose? There's just no letter for that. There's not really any reason. It's just that it didn't get specified. And we can't change it now. So maybe we should do better this time. Should these numbers be 32-bit or 64-bit? That's a huge question that people have trouble with. Some operations aren't fully specified. Like if you want to do an outer product, you can't add it, you have to overwrite. Or no, let's see what it is. You can only add it, you cannot overwrite. So you have to do you have to zero it out first. Things like this. These aren't game changers, but it's things that we wish you could have done better. And perhaps there are things also that would allow the implementation to be more efficient. One of the example of these is we have these LDA things. And if you're not familiar with what that is, basically this is, if we have a matrix, we assume that in each column we go down, and in memory, to go from one element to the next, it's just the next one in memory. So that's called a stride 1. To go from one column to the next, we use this LDA parameter. And the columns could be right next to each other in memory, or they could be widely spaced. But why does it have to be that way? Why does it have to be column major? Why couldn't it be row major? Okay, C-BLAS maybe takes care of a little bit of this, but you can't mix them. And why do the columns have to be contiguous? Why can't you just have whatever number you want there? So what if we could have more flexibility here that would allow you to implement things on top of this and take advantage of this and take advantage of the efficiency? And then there's, of course, things about const correctness, aliasing, mixed precision, mixed domain, all sorts of things that could be incorporated. So here is my suggestion of a BLAS for tensors. Basically, you take what's in the gem in the BLAS call, and you map it to what's in the tensor. Okay? So whereas a matrix multiplication has dimensions m, n, and k, a tensor contraction would have some number of dimensions in each of those categories with their individual lengths. Alpha and beta, of course, stay the same. And your matrices, your tensors, of course, have a pointer because they have to live somewhere in memory. And again, it's the same thing with the lengths. Instead of having a single, LDA or stride, or whatever you want to call it, you have some number that tells you how this tensor is laid out for each dimension. It's very logical, very, it's simple. This dimension is this long, and to go from one element to the next, you have to go this far in memory. That's basically all it says. So this is actually an interface that I have implemented on top of tensor contractions. And it's actually very, very handy because this is exactly the kind of information that you need when you're writing the implementation of a tensor contraction. It's not just that it's handy for a person using this interface, it's handy for the implementation, the computer, to actually make use of that information and do some computations. So it does double duty there. But can we do better? What if we could do something that is actually easier for people to use? Because if you look at the interface in the previous slide, this is a lot of data to specify every time you call this function. You have to have all these arrays laying around, you have to manipulate them and put them in the right order, in the right place. And okay, these are the right arrays to do one type of tensor contraction. For the next type, you'd have to make new arrays and fill them up and not make mistakes and things like that. And of course, interfaces, layered above this can help you a lot there, but there's still a lot of room for error here. So how can we do better? So one idea is to say, instead of specifying the operation as our main priority, why don't we specify the objects as our main priority? What do these tensors look like? And then after we specified that, then we can specify what we're going to do with them. So now we have a group of arguments for each tensor. We have where it is, how many dimensions does it have, how long is each dimension, what's the layout, what's the strides, and then we have, are we going to conjugate it, because we have to worry about complex numbers. And that's it. So for every tensor, we have those arguments. And that describes everything about that tensor, and that's not going to change. From one call to the next, it's the same thing. So you can make way fewer errors. You can wrap that up in a nice object-oriented interface. So it's much easier to specify that information. And then we have these string parameters, IDX-A, IDX-B, IDX-C. What are those? What do those do? So if you look at this example here of a tensor contraction, it's exactly what you write when you write down the math. Exactly. IDX-A is just the letters, K, M, N, I. It's just exactly what you write down if you write this on a whiteboard. And the interface then figures out, okay, these indices appear in both of the inputs, so I need to sum over those and then multiply over those and then add together and that kind of thing. And so it can figure out what to do fairly easily, and you don't have to worry about it. All you have to do is specify, what do I have, and what am I going to do with it? And so actually when you use this interface, which is the working interface that I use a lot, it's extremely simple to take tensor contractions on the whiteboard, put them into code, and have them work exactly the way you want. But what else does this allow us to do? This allows us to go beyond tensor contraction. So with matrices, basically you want to multiply them. There's not a lot else you want to do. I mean, you want to do triangular solves and QBAR and that kind of stuff, right? But with tensors, that's not as relevant. But when we have all these extra dimensions, there are a lot of really neat things we can do with this data, a lot of neat operations, and we can actually compose these operations together. So whereas we have contraction, so contraction is specified by we have some index, in this case B, which is shared between two of the tensors. That means we multiply. Shared means multiply, and then we add them all up, and that's contraction. The outer product, of course, is if we don't have any shared dimensions, we're just multiplying and not adding. But then we can get really interesting things like replication. If we all of a sudden put this index in the output that doesn't appear anywhere else, it means we're going to take the data and we're going to put there multiple times. We're going to broadcast it. The same thing if you have an index in one of the inputs that doesn't appear in the output, you can sum over that without multiplication. It's a trace. And then you have things like weighting. So if your index appears in both inputs, remember that means multiplication. But if it appears also in the output, that's a contraction plus a broadcast, and you can just forget the sum part. So you just multiply with no sum. So these are all the elements. We have multiplication of things, we have adding things up, we have broadcasting things. And in fact, there are 7 categories in all. And so what you can do is from these very human-readable, very easy to understand strings, you can figure out what these 7 categories are and tell the computer to do exactly that. And then what you can do is you can actually put these interfaces together. So you take your nice string-based, object-based interface on the top, you just do some bookkeeping stuff, dump that on the bottom, so now the user's happy, the implementation designers are happy, everybody's happy. So that's my vision of a tensor BLAS. But that doesn't really help if it doesn't do anything, because this is just an interface. You have to have an implementation of this. So what implementation are we going to use? And specifically, how can we do this without the BLAS? So how do people do tensor contractions today, right now? The main way people do this is what's called the TTDT approach. What this stands for is transpose, transpose, degem, transpose. And I say degem because as a chemist, if it's not double precision, it doesn't exist. So what you have to do is you have to take your tensor and you have to move it around in memory. You have to do what's called a tensor transpose. And you have to lay it out in memory just right so that you can pretend it's a matrix for just a little bit. And you pretend it's a matrix for just long enough to do a matrix multiplication, you call BLAS, And then you transpose things back around and you get your output. And so it's a neat trick. On the outside, it looks like tensors, and the inside it looks like a matrix. But you have to do this transpose step. And this is problematic for several reasons. For one reason, it means that you have to use twice as much memory, because you have to copy the whole thing. You have to do a lot more memory movement, which is expensive, and it's getting more expensive all the time. Moving data around does not thread well, does not parallelize well, because you have a limited amount of bandwidth. And it's really an implementation detail that the user doesn't want to know about. Because if you're going to suddenly use twice as much memory, maybe some people don't care, but other people are like, I want to know about that, and I don't want you to do that. Or they want to specify their own buffers or things like that. It gets very complicated. Now, the other way to do it is to say that, okay, instead of taking the entire tensor and moving things around and pretending this is a matrix, what we can do is we can take our tensors and we can pull out a little tiny bit of it and take that as a matrix. Basically, what you do is you take the innermost dimensions of each tensor, and you put those together, and then you do a matrix multiplication on those. But then you have to do a lot of matrix multiplications, because there's all these other dimensions laying around that you have to deal with, and you have to loop over them. So not only do you get matrix multiplications that are very small and hence inefficient, but you have to worry about what order am I going to loop over these dimensions in, which makes a huge difference to how you use your caches and things like that. And then you start worrying about, okay, well, in my inner kernel, are things packed together closely in memory? Am I using full cache lines? All these things that people don't want to worry about, but make a big difference in the end. And actually, it's kind of funny. If you start caring about all these things and doing everything the right way, you actually wind up with something, which is what I'm going to talk about later, which is not even this at all. So this is like the wrong way to do the right thing, which is what I'm going to talk about. And so why does this matter? So we do some transposes, whatever. So here are some actual numbers from some quantum chemistry runs that I've done. And so if you look at the very bottom line, we have performance breakdowns of parts of these calculations. And so if you look, it's spending about half of its time doing degen, it's level 3 BLAS, which is okay, But it's spending between 25 and 40% of its time just doing tensor transpose, which we really don't want to have to do at all, and we're forced to do it. And this is just one core. You go to multiple cores, that balloons. And then it's also spending a lot of time doing this level 1 and level 2 BLAS. And actually, the dirty secret I didn't tell you on the previous slide is when you do these loops over your degens, sometimes they're not degens. Sometimes they're matrix vector multiplication. Sometimes they're vector-vector addition. And so you wind up a lot of time doing that, which is definitely not efficient. So what can we do instead? So one thing that we've developed in our group here at UT Austin is called the BLIS library. Basically what it does is it implements matrix multiplication in a way in which only a very, very teeny part of it, the part at the very bottom, has to be written in assembly. Whereas before you'd have tens of thousands of lines in assembly. So we have about 500 lines of assembly for any given architecture. The rest of it is this nice clean C, or I've written a C++ version. We also have a Rust version. So it's actually not that hard to write the rest of it. And it goes very fast, as you'll see in a second. So what can we do for tensors now? So all we have to do to make tensor contraction out of matrix multiplication is do what we did before and pretend that they're matrices. The trick is, this time we're going to pretend, but we're not going to move the data. We're going to pretend, and then when we're forced to move the data, that is when we're going to put this into contiguous memory, or we're going to write something back out to the output, only then do we actually know that it's a tensor and get the data from the right place. It's the only time. And so there's two things here. Number one, I can reuse a huge amount of code, a huge amount of literature and research in the computer science community about how to do matrix multiplication fast. All I have to do is write a few little bits of code, and bam, I have tensor contraction. So how does this work? Turns out it works really well. So let me break this down for you. So the two graphs on the left are running on one core, single-threaded results. The two graphs on the right are running on 8 cores. And these are running on Intel's Ivy Bridge Xeon, I think it's 2.4 gigahertz, something like that. And the purple line at the top is MKL doing just a matrix multiplication. So that's basically the speed of light. You can't really go faster than MKL doing a giant square matrix multiplication. You just can't do it. So the line right below that, the green line is BLIS, which is our library, doing the same thing, matrix multiplication. So it's not quite as fast as MKL, but then again, we don't have billions of dollars, so that's okay. It's about 5% slower. And there are also other things that we could do to close that gap. So that's fine. The yellow line then is going to be tensor contraction the old way, using the transpose, dgem, and transpose. And as you can see, it's a lot slower. It goes from acceptably slower to unacceptably slower, and everywhere in between. And then we come back in with this blue line, which is my code doing tensor contraction, the exact same thing. And lo and behold, it's almost exactly as fast as dgem. So yes, you can make this work. And you don't have to use more memory, and you don't have to make users mad and that kind of things. So yes, we can define an interface to do tensor contractions. That's easy for me to write code for, or someone else to write code for. And it's easy for people to use, to build interfaces on top of, hopefully in languages like Python. And it's fast. So hopefully it satisfies everybody. And so in the future, what I want to do is extend this even more. We do mixed domain, mixed precision, and define interfaces for that people can do, so that you don't have to waste time saying, for example, doing everything in double precision complex all the time. Worrying about things that I care about in chemistry, like symmetry and blocking and different tensor structures and things like that. And then defining more generic building blocks at this kind of low level that people can use, that people can get excited about, and that can be efficient and help people sort of all across the board. So I'd like to thank the people in my group, especially the people on the bottom who do work on BLIS and have helped me with my tensor stuff. Some links to the code and some papers, and a big thank you to the organizers and everyone here for listening to my talk. Thank you.
How would you compare your work to the work that Google's doing with TensorFlow? Because I'm looking at the list here, and there's a huge number of operations that they have scaling from handheld devices all the way through to Pascal, NVIDIA, Uber Elite chips.
So from what I know of TensorFlow, is they've addressed the problem of data movement and data flows and offloading and things like that very well. But at the very low level, what you actually do to, when you're worrying about caches and registers, things like that, is not very well optimized. I haven't looked at the code specifically, so I don't know if they're doing matrix-based approaches. I know I've read some papers that certainly were matrix-based. Some of them were this loop over gem approach. Those are the two main ones I've seen. But basically, this is a way to transparently replace all of that. You could take all the great stuff that TensorFlow already has and make low-level stuff faster. So I think it's very synergistic.
I'm trying to understand your approach better. I think is it the understanding that is compared to the BLAS approach, you don't move the data until it's necessary. So you're doing some lazy data movement or copying only when you figure out that the tensor are not contiguous, the dimension of the are not contiguous, then you move the data. Is it?
So it's actually a little bit simpler than that. What I actually do is if I'm thinking logically of this as a tensor, right?
Right.
What I do is I imbue this tensor with a data layout, which happens to match the layout of the tensor.
Okay.
And so I don't even actually think of it as a tensor. It's just a matrix with a special data layout. And so everything operates exactly the same as if it was a regular tensor. I move the data at the same time in the same way. It's just the data comes from a different place because of the different layout. And there's just some logic to handle that.
And you have some assembly code, so what are it used for? Why do you need assembly?
So the assembly code comes at the very low level. Basically what you're doing there is you're doing like a 6x8 or a 4x6 or something like that in the registers, and you're doing a whole bunch of them. And it just has to be done in assembly, or sometimes intrinsics, and there's just no way around that.
Okay.
But it's only a few hundred lines, and I don't have to write it. It's already written.
All right, so I don't do tensor math, but I do work with multidimensional arrays a lot, and the biggest problem for me is slicing and accessing different dimensions across the X dimension, or Y dimension, or Z dimension. And what I was wondering is, do you think that changing the approach of how you're interfacing with BLAS could potentially address that issue of indexing or accessing different portions of a three-dimensional matrix, for example?
Well, there's two parts to that. There's number one, there's the interface aspect of that. And number two, there's the computational aspect. So it depends what you want to do. If you want to take a slice out and do an operation with that, that is something where this comes in, definitely. But in terms of, I just want to know, okay, what is the data along this slice? That's more of an interface issue. And so I know certainly in C++, there are a lot of alternatives for this. In Python, of course, there's NumPy and things like that. As in terms in terms of a universal interface that everyone implements, we're a long way from that.
Last one, sparseness. Sparseness. I work with second, third, first order tensors in geophysics. All our higher order tensors, they're very sparse. Otherwise, you can't do anything.
Right. So the difficulty there is, so what I've done relies on the fact that you can take a tensor and you can pretend it's a matrix, and you can have a matrix layout such that you actually get the tensor. Doing that for sparse things is a little more difficult because the sparse representations are more specific to it being a matrix. So if you could define a sparse representation which would map from tensors to matrices, I think that would go a long ways to solving that problem.